Alright, today we're going to have a look at separable first order differential equations. Now these titles are starting to get very, very long. In fact, at uni I had an entire course called Partial Higher Order Differential Equations, and then a lecture that was called Separable First Order Partial Differential Equations. So they're getting at quite long concepts, but that doesn't necessarily mean they're tricky, they're just long titles. So a first order differential equation is called, it's called separable if it can be written as a product of a function of x and a function of y. In other words, y dash can be written as f of x times g of y. So let's check whether these equations are separable. So this here we can see is a function of x times by a function of y. They're divided, but really we're just timesing by 1 over 5x cubed. So yes, this is separable. This equation, no, it is not separable because there's a plus here. No matter what we do, it's never going to be a function of x times by a function of y. Part C, yes, this is separable because if I plus 2y to the other side and divide by x, then I'm getting dy dx is 2y on x. So yes, this is separable. Now to solve separable first order differential equations, we do the following. We simply divide the y terms over to the left-hand side and integrate both sides. Often we're going to see ln's a lot in these solutions. So we're going to learn how to do all of those steps in these next few examples. So before we can solve it using this method, we have to ask ourselves, is this a separable differential equation? Yes, it is, because it is the product of an x function and a y function. So solve y dash equals minus 2x e to the y. To do that, we're going to divide the e to the y to the other side, and it's equal to minus 2x. We're then going to say, okay, this is equal to minus e to the y dash, and that's equal to minus 2x. Now we can't integrate this at the moment, because we've got minus e to the y times by y dash. But we're going to remind ourselves that y dash means dy to x. So I can say this is minus e to the y dy to x equals minus 2x. And then we can integrate both of these, and we're going to integrate both of these with respect to x. We're not allowed to integrate two sides of an equation with respect to two different variables, but we can integrate on both sides with respect to the same variable. So we can cancel that and that, and we get this is equal to integral of e to the minus y dy is equal to the integral of minus 2x dx. Would you do that many steps normally? No, you would likely go from here straight away to the step after this. But this is just for our first example of how to do this. Now the integral of e to the minus y is minus e to the minus y, and that's equal to minus x squared plus c. Now we can cancel the negative from both sides, so this is e to the minus y equals x squared plus c. Now often before we do the transformation to with the ln, because we want to make y the subject, we're going to find that constant c. So we're looking at the solution through 0, 0. So e to the 0 is equal to 0 squared plus c. And e to the 0 is 1, so that means c equals 1. So this equation is e to the minus y equals x squared plus 1, which means minus y equals ln of x squared plus 1, which means y is equal to minus ln of x squared plus 1. So that was part B over here. I should have made that clear. And part A would be the solution without the plus constant c. So we would be solving it and we would get to, it would just be this answer here, but there would be a plus constant c in there. All right, so that's how we solve these differential equations. And yeah, just to recap, I might just put the answer to part A down here. The answer for part A would be y equals minus ln of x squared plus c. So that would be our general solution, and this would be a particular solution. Okay. Example number 3. We're going to solve the equation y dash equals x on y. We're going to ask ourselves, is this a separable differential equation? Yes, it is, because it's a product of x and 1 on y. It's first order as well, which means we can use this process we've been using, because the highest power is y, the highest derivative is y dash. So this would be y dash equals x. We can say this is equal to the integral of y dy, which is equal to the integral of x dx. Again, we don't need to show all of those steps. We can just go straight to here. And the integral of y is y squared on 2, so a half y squared, and that's equal to x squared on 2 plus c. And also, don't be that person who puts different constants on either side. We don't need plus c1 and plus c2. Just put plus c on one side. It doesn't matter. So, it's not quite clear how they want their solution. I guess if you wanted to make y the subject, well, we could say that this is equal to y squared is equal to x squared on 2, sorry, x squared plus c. We've still got that plus constant c. Some people like to change it to say a constant d, but it's just the same thing. Or you could say c1 here and c2 there, whatever you like. So yeah, it's not clear how they want the solution. That's technically the solution. You could make y the subject by square rooting it, but we might just leave it like that. Part B, find the solution passing through 4, 5. So 4, 5, well, we're going to say 25 is equal to 16 plus that second constant, which means the constant 2 is equal to 9. So therefore, a particular solution is y squared is equal to x squared plus 9. Now, I guess if you wanted to, you could express it. I think that's some sort of ellipse, this equation, x squared, y squared minus x squared equals 9. I think it's an ellipse. That might look like that type of equation. But we don't need to know that. Okay. Now, constants, we can have constants as solutions to these differential equations. So when we differentiate a constant, we get 0. We know that and we're aware of that. So when the derivative of a differential equation is equal to 0, that means a particular constant is the solution to an equation because it's been differentiated to get 0. So therefore, any value of y that makes the derivative 0 is a constant solution to the differential equation. So for example, in y dash equals minus xy squared, y equals 0 would make this equal to 0, and hence y equals 0 is the solution to that equation. In this second example, y equals 1 would make this 0, which means y equals 1 is a solution to this differential equation. When we looked at slope fields in the previous video, y equals 1 would be those horizontal lines on this, horizontal isosceles, which would correspond to horizontal line elements on your slope field. So we're solving y dash equals minus xy squared. So we might notice, first of all, that y equals 0 would be a solution to this equation. So y equals 0 is a solution to this equation. And we call that a trivial solution. Y equals 0 is a trivial solution to this equation because it makes the derivative 0. Let's have a go at solving this normally though. So we're going to say that we might divide the y squared over and say y to the minus 2y dash is equal to, oh, I need more room there. What can I do? I add this, add another page in. Y to the minus 2 is equal to minus x, which means the integral of y to the minus 2 to y is equal to minus x, or the integral of minus x dx. Now, of course, integral of minus 2, y to the minus 2 is minus y to the minus 1, and that's equal to minus x squared on 2 plus c. We might cancel those minuses, so we might say y to the minus 1 is equal to x squared on 2 plus c. And that's our solution there. You could say 1 on y equals x squared on 2 plus c. Not really necessary. It doesn't specify. And it doesn't really matter for your particular solution, for your general solution, because usually we're just going to use this to find the particular solution. So you could say this here, x squared plus, we call this c1, plus c2 on 2 is equal to y to the minus 1. And then you could say y, flipping everything over, is 2 on x squared plus c2. You could say x squared plus 2 lots of c1 if you wanted to, but it's just a constant, so it doesn't really matter. So that would be like... Part B then asks us to find a particular solution through y1 equals a half. So we're going to say a half is equal to 2 over x squared plus c2. Now I think that would give me, 3. Let's just confirm that. So flip both upside down. So 2 is equal to x, or x is 1, in this. 2 on 1 plus c2. So 1 plus that constant 2 on 2. Times it up there, c2, equals 3. So therefore that particular solution is y is equal to 2 on x squared plus 3. That's part 1. Now part 2 I think I remember was a bit funny. Y2 is equal to 0. So our general solution was that y is equal to 2 over x squared plus some constant. And we're substituting in the condition y2 equals 0. So 0 is equal to 2 on 0 is equal to 2 over 2 squared is 4 plus c2. If we flip this upside down, we're going to get 0 is equal to c2 plus 4 on 2. Now I'm getting c2 is equal to minus 4. However, there is a problem with this question. So that will give us that c2 is equal to minus 4. But we have to think, is that possible? Is that allowed? If c2 was minus 4, then on this particular solution, we're going to get 4 minus 4, which is 0, which means we would be dividing by 0. So this solution is not actually allowed. This is not actually a solution. However, so y2 equals 0 is not a solution because of dividing by 0, but the first condition of the question that we initially wrote was that y equals 0 is a solution. So therefore, since y0 is a solution, that means y2 equals 0 is a required solution. It just doesn't have a constant. It's going to be an asymptote of this graph, but it's still a solution to the differential equation. And that's because it's a trivial solution, one of those constant solutions. Okay. Last two examples. So we're solving the equation y dash is equal to x 1 minus y. So first of all, this is a first order differential equation because the highest derivative is the first derivative, and it's separable because it's a product of a function of x and a function of y. So we're going to divide this over and say this is 1 over 1 minus y times by y dash is equal to x. Then we can say this is the integral of 1 over 1 minus y dy is equal to the integral of x dx. Now the integral of 1 over 1 minus y is simply the natural logarithm of 1 minus y, and this is equal to x squared on 2 plus c. Now we also need to consider the fact that if we differentiate 1 minus y, we get minus 1. So because of that, we need to put a minus out here. So because the differentiation of 1 minus y is minus 1, so we need a minus here and a minus there. Now what I might do is I might just put the negative over there to make it a bit easier. Okay. So we haven't quite found the solution yet because we need to make y the subject to find this particular solution. So we're going to take the e of both sides and say so example number 5 asks us to solve the differential equation y dash is equal to x times by 1 minus y. Now first of all, this is a first order differential equation, and that's because the highest derivative is the first derivative, y dash. It's also separable because we've got a function of x times by a function of y. So to solve these separable differential equations, we're first of all going to divide by 1 minus y to get it over to the other side. So 1 over 1 minus y, y dash, is equal to x. Now, we have to consider that we are going to eventually want to make y the subject of this equation. So we might multiply everything by minus 1 and say that this is 1 over y minus 1 y dash is equal to minus x. We're now going to integrate both sides. The integral of 1 over y minus 1 is ln of y minus 1. And the integral of minus x is x squared on 2 plus c. We still though need to make y the subject of this equation. So what we're going to do is we're going to take the e of both sides. So y minus 1, e to the power of a logarithm is just the thing inside the brackets. So this is equal to e to the minus x squared on 2 plus c. Okay. We're then going to remind ourselves, okay, we do have an absolute value there. Generally though, what we do with these equations is, since we have a plus c here, we've seen this last in year 11 in our work with exponential growth and decay. When we've got a plus c there, we can write this as e to the c, e to the minus x squared on 2. But then we say let e to the c equal a. So y minus 1 is equal to a e to the minus x squared on 2. And then we're going to plus 1 to the other side and go y is equal to a e to the minus x squared on 2 plus 1. Okay, so that's the solution to part A. We're now going to have a go at solving part B. So part B, we've got to find the particular solution passing through the origin. So we're looking at the particular solution passing through the point 0, 0. So 0 is equal to a e to the 0 squared, which is 0 on 2, plus 1. Now, of course, that means a is equal to minus 1. So therefore the solution is y is equal to minus e to the minus x squared on 2 plus 1. And part 2, we're looking at the particular solution through 1, 1. So 1 is equal to e to the, or ae to the minus 1 squared on 2, which is minus a half, plus 1. Now, of course, if we minus 1 to the other side, that's just going to get a equals 0. So therefore, the solution is y is equal to 0 e to the minus x squared on 2 plus 1. And 0 times that is 0, so y is equal to 1. So this is a constant solution, which is y is equal to 1. Now, we can see that from the initial question, because if you made y equal to 1 in this question, you're going to get y dash is equal to 0, so therefore y equals 1 is a solution. So that idea of finding the constant solutions can be a fast way of finding constant solutions through the equation. Okay. The last example in this question is dealing with absolute values, and we're going to have a look at solving y dash equals xy. So the reason we need to deal with absolute values is because when you integrate 1 on y, you need to say that it's the absolute value of ln of y, because it needs to be positive. So we might first of all state that y equals 0 is a trivial solution, and that's because y equals 0 would make this equal to 0. So part A, we're going to solve 1 on y, y dash is equal to x. So we divided the y over because this is a separable first order differential equation. It's also linear. So the natural logarithm of y is equal to x squared on 2. Take the e of both sides, or plus c, sorry. So y is equal to e to the x squared on 2 plus c. But remember, when I've got that plus c, I let e to the c equal to a. So y is equal to a, e to the x squared on 2. Okay, so that's our general solution there. Part B, question B, part I asks us to find the particular solution through x is 2, y is 3. So 3 is equal to a, e to the 4 squared, what are we doing? Equal to, we're putting in 3. So we're going, oh no, 4, we're putting in 2, so 4 squared on 2 is 2. So we're having a look at what is the value of a. Let's divide the e squared over. Now we're getting 3 on e squared, which is 3e to the minus 2. So therefore, this particular solution through this point is 3e to the minus 2, e to the x squared on 2, which you could simplify and say this is 3e to the x squared on 2 minus 2. So really our constant is minus 2. Okay, part 2. The solution for which it's equal to 0. Okay, so we've already said that y equals 0 is a particular solution. So this is equal to 0 when y is equal to 0. So therefore, the solution is y equals 0. Alright, and that's separable first order differential equations. Thank you.